So now let me revisit the Slater's rule for matrix element, and in particular of course for expectation value. So we wrote down this where psi is chi1, chi2 to chi_n. Remember, whenever I am writing this is a determinant with a 1 by square root n factorial. So I must mention that this is in full form, it is 1 by square root n factorial, and then a determinant which looks like this, chi11, chi12 to chi1n, chi21, chi22, chi2n, and so on till chi_n1, chi_n. So whenever I am writing this abridged form, this essentially maps into this. So please remember this, including the 1 by square root n factorial. Okay. So this is basically a normalized wave function. I wrote down the Hamiltonian, which was sum over h of I plus 1 by r. Okay. So our matrix element was, now you add, this was the matrix A.1 and A.2, A.1 plus A.2. So can you tell the first term? Sum over summation I chi h chi, right? That is the first term. Note that these i's are indices for spin orbitals. These are not coordinates of electron. Coordinate of electron is only 1, and that is a dummy variable. So whether it is electron 1, electron 2, electron 3 does not matter. The n spin orbitals actually take care of n electrons. Okay. Then you have the next term, which is, tell in any one form, whichever form you remember. Half of, okay, that is one form, half of summation all I all j, all I all j, I less than j. Then half won't be there. If it is half, it must be all I all j, correct? So then this is 2 electron integrals chi I chi j 1 by r12 chi I chi j minus chi I chi j 1 by r12 chi j chi. So this is 2 electron integral 1 and 2. These are coordinates of the electron. These are again indices of the spin orbital. And these have 1 and 2 which should match with these coordinates of the electrons. If you write by chance 1 by r2 3, somebody can write that, then it is assumed that this is 2, this is 3, this is 2, this is 3. I hope it is clear. This is a dummy variable, it does not matter. At the end of this, integral will not depend on the coordinate of the electron, but the integral will depend on which spin orbital it is, because each spin orbital is a different function. So that is why it is dependent on spin orbital and not on the coordinate of the electron. I again repeat, so that there is no confusion. This is called the Coulomb integral and this is the exchange integral, right? The same thing can also be written in a form which is computationally simpler because it does less job, I less than j, chi I chi j 1 by r12 chi I chi j minus chi I chi j 1 by r12 chi j chi I. And we noted why it is so, because for I equal to j the entire term is 0. Of course, each of them is not 0, but the entire term is 0, and for I less than j and I greater than j, they are identical. Okay, so I can write only one term and knock off this half. So half into 2 becomes 1. Is it clear? Because of the symmetry. If I and j are interchange, each of the integrals remains the same. So, some of the symmetries you must understand. So, the symmetry of the 2 electron integrals, if I have chi I chi j 1 by R12 chi I chi j, that is identical to chi j chi I 1 by R12 chi j chi I. Correct? If I interchange both left and the right side, both. Here for example, they are not same because I have interchanged only one pair in the right. So, it produces a different integral. Why are they same? This has 1, this has 1, this has 2, this has 2. In this case, this has become 1 and this has become 2. But they are identical because this is not because I and j can be interchanged, but 1 and 2 can be interchanged. So, instead of chi I 2, I can always call it chi I 1. But then you will say that this also has to be interchanged, which is correct. I can make R12 and that is equal to R21. So, if I interchange this, it is actually identical. So, that is the reason this symmetry is there, not because I and j can be interchanged. Remember, chi I and chi j are different spin orbitals, but they come because the coordinate interchange is actually assumed. It is sometimes not obvious because I am not interchanging this, but this is actually implied that it is R21 because R12 is same as R21, and that is why all these integrals for I less than j and I greater than j, both Coulomb and exchange together are equal. Each of them is equal. So, I can write only one pair. Is it clear? I mean, at this stage, please understand the symmetry, they are very, very important. Computationally, you would like to have this because the number of loops, please remember in computer, loops are very important. How many operations you are doing? Number of operations that you are doing is NC2. Here, the number of operations that you are doing is n square, right? Each I going to 1 to n, j going to 1 to n. So, n into n. N square, this is NC2. So, this is obviously less. In the other point is that even here, when the number of operations are less, you are again multiplying by 0.5, which is an additional operation for each of them. So, it is actually in all senses, it is a bad formula to program. Okay. So, it is good to of course understand that this is how it came. Further, a technical term I am going to introduce. Chi I chi j, now I am not going to write 1 by R12. I will write a double bar chi I chi j. I am introducing a term which will simplify the algebra later as chi I chi j 1 by R12 chi I chi j, which is the Coulomb integral, minus chi I chi j 1 by R12 chi j chi I. This entire part, Coulomb minus exchange, I am giving a new nomenclature, so that I do not have to write each time. Please understand, this is only for simplification. This integral is also a 2 electron integral. I am not deliberately writing 1 by R12, but there is a double bar and assume that there is a 1 by R12, but it is not like a regular integral. So, it has to be given a different form. So, it is Coulomb minus exchange. The exchange that I am doing on the right side is implied here whenever I am writing this. So, it is actually a combination of two terms. So, don't interpret this as just Coulomb. Okay. So, this is a very special symbol that I am introducing. This symbol, and I will explain why it is called so, is called anti-symmetrized 2 electron integral. Of course, these are 2 electron integral. These are anti-symmetrized 2 electron integral, and I will just now tell you why it is anti-symmetrized. Okay. So, this anti-symmetry essentially means that if I take this double bar integral, which is Coulomb minus exchange, and then interchange only one side of it, right hand side, this will actually become negative of itself. Remember, for each of this integral, if I interchange the right side, it is not negative or anything, it is different. That is how I got Coulomb and exchange. But for the anti-symmetrized integral, when I exchange, this is negative, which can be very easily seen, because this is nothing but now the Coulomb of chi I chi j chi j chi I, which is this, minus the exchange. So, the sign is exactly opposite. Okay. So, I hope you can see that this is now negative of this. which was not true for each of these integrals. They were different because in this case, this is this minus this. In this case, now chi j chi I will come first with a plus sign and then its exchange, which is chi I chi j with a minus sign. So they are negative of each other. I hope everybody is convinced. So if anybody has a problem in the algebra, please tell me. And that is the reason it is called anti-symmetrized, which means if I interchange one of the pairs, it is negative of itself. Okay, just like our wave function. When I interchange two coordinates of pair of electron, it becomes negative. So just like this. But interchange here only on one side. If I interchange two sides, it does not help. It will get back the same integral. You can quickly see here. It doesn't help because each of them remains same. So it does not matter. Of course, I could interchange also the left pair similarly. So this is negative of chi j chi I, chi j, and it is same as interchanging both chi j chi I, chi j chi I. Is it clear? So each pair of interchange either on the left and the right produces a minus sign. So if I interchange twice, both left and the right, it will come back to the same thing. And please practice these integrals. If you write this, what will happen? This will become chi j chi I, which is same as this. Because I already told you that each of the integral I can interchange. Then minus the exchange, which is again the same of this. So this is actually exactly same as this. But if I interchange one side, it will give a negative sign because the exchange will become plus, Coulomb will come with a minus sign. These are very simple mathematics, arithmetic actually, just practice this so that you have no confusion. So many times we like to write this only to simplify this, and it also has a very specific, in this form it has a very specific symmetry, that antisymmetry. So that may be exploited at some point of time. But the Coulomb and the exchange are not explicitly seen. Here, for example, the Coulomb and the exchange are explicitly seen. So that part you have to assume, but that's not very difficult. Okay? So the same form one can write now as, so I can write this psi a psi as in a more simpler form as sum over I chi I h chi I plus I less than j chi I chi j anti-symmetrized chi I chi j. That's it. So in a more simple form. So I take NC2 pairs of Ij spin orbitals. Remember, these pairs are again not of the electron coordinates. But whenever I am taking spin orbital pair, physically actually I am generating electron pair. It's one and the same. Because I have n electrons in n spin orbitals. Instead of looking at electron pairs, I am looking at spin orbital pairs, which tells me where the electrons are. So all pairs antisymmetrized. This antisymmetrized element now contains the Coulomb and the exchange explicitly. So I am not writing it each time. Is it clear? These are again for some standard, in a simple way to write the energies. So this is the energy that you have for a wave function which has n spin orbitals. Okay? Is it clear? Because eventually, of course, you have to start doing a variation. Remember, our objective of Hartree-Fock is to make this minimum subject to a condition that the chi I chi j should be equal to delta Ij. Okay, so that we will do. So, so that the form should be very clear. So we'll take a pause here and look at this form little bit more critically for specific determinants. So let me take some specific determinants and analyze them. This energy, whatever the chi, of course the chi's will be obtained for Hartree-Fock. The chi's will be obtained, as I told you, after variation. Okay, the other class I discussed the variation theorem will actually give you chi. I still don't know the basis. Okay, but let's assume whatever is my chi I, if I know chi I's, this is the energy in terms of chi I's. Okay, so we will try to analyze this form little bit more critically, and actually there will be a lot of good physics that we can see from there. So let's look at a determinant which is closed shell. Okay, there are many times in this course we will actually look at closed shell. So what is closed shell? Let me again define what is closed shell. I have defined this in 425. So let me again define closed shell very properly. So first of all, number of electrons or number of spin orbitals is even. That is very important. You can talk in number of spin orbitals because it's a determinant, so that means number of electrons. So that's even. So n is even. Out of this, n by 2 spin orbitals are alpha spin, and the rest of the n by 2 spin orbitals are beta spin. Is it clear? Because each spin orbital has a spin part and a space part. So the spin part, half of them is alpha spin, half of them is beta spin. Now when I am discussing spin orbitals, it is very clear how the electrons are oriented. If spin orbital is alpha spin, that means electron in that orbital is up spin. So that is very clear from the discussion. Then each of these spin orbitals has a space part. So that's number 1. This is number 2. Then the number 3 is that the space parts of n by 2 alpha spin orbitals are identical to the n by 2 beta spin orbitals. So they are actually identical. So the space part of the n by 2 alpha spin orbitals completely overlap with the space part of the beta spin orbitals. Is it clear? These 3 together is called closed shell. I mean, you have an idea of a closed shell, doubly occupied. Now you will see that this is exactly what we are seeing. I am just giving a more sophisticated language without bringing in electrons. Everything in terms of spin orbitals, because spin orbitals define my determinant. Remember, if I have n spin orbitals for a single determinant, it automatically means it is n electron. I don't have to talk about n electrons. And how these n spin orbitals are chosen, that defines your closed shell. And this is your common definition of closed shell. Nothing new, but you can check up. All right. So many times in this course, we'll actually be defining closed shells. So we'll write Hartree-Fock also initially for closed shells. The closed shells are many systems that we deal with are closed shell. Of course, there are many systems which are not closed shells, which are open cells, radical, these, excited states, triplet, lots of things are there. So what is open shell? Open shell definition is very simple. Whatever is not closed shell. So now you don't have to define it. Right? So whatever is not closed shell is an open shell, which means any of these 3 are violated, it's an open shell. But remember, closed shell is not either of these 3, this plus this plus this. So if one of them is violated, it's already an open shell. For example, if n is odd, it can never be closed shell. Don't even discuss the second and third. Okay? Now after that, what kind of open shell? That will depend on 2 and 3. But at least it's not a closed shell if n is odd. So right away discussion ends. And many times we know they are doublet, everything else. Then 2 and 3 will define what kind of open shell it is, if n is odd. So there you will see there is a restricted, open, unrestricted. We will come to those points when we discuss open shell, okay, depending on what kind of space parts. But at this point, for my discussion, it is sufficient to say that anything that is not closed shell is open shell. I will not define any more open shell. Okay? There are only 2 things, either closed or open. So obviously, if anything that is not closed is open. So let us now take up a closed shell determinant. And let us see what happens to the spin orbitals. So when I say I know the spin orbitals, what does that mean now? That means I know the space parts. Because what is spin orbital in this case? It is just space part into alpha and beta. So I know the space parts. So let us say that I know the space part. So chi1 is phi 1 alpha, chi2 is phi 1 beta, and so on. Chi3 is phi 2 alpha, and so on, right? chi 4 is phi 2 beta and so on. So I know phi 1, phi 2 up to phi n by 2. Is it clear? Because I require n by 2 space orbitals to form the n spin orbitals for closed shell, because all I need to do is to attach alpha or beta to each of them. So I will double the number of spin orbitals. Is it clear to everybody? So that means this is known to us. In fact, when we will do Hartree-Fock for closed shell, this is exactly what we will find out. Because I know that these are alpha beta. So the real variables will not be chi, the real variables will be phi. But at this point I am avoiding this question, how we will get phi. Let's assume that I know phi's, hence I know the chi's, correct? And now I am applying my energy formula, Slater rules. Okay, so let's write this Slater rules. Energy, again a sum over I. First I have to write over spin orbitals, chi I h chi I, plus, you can do half, let's see, half ij, chi j. I will write it specifically in full form for the time being, minus chi j 1 by r1 to chi j. What I want to do now is to transform this energy into the space orbitals. To do this, what do I have to do? I have to integrate over the spin coordinate only. Remember, these coordinates of the spin orbitals are space and spin part. Although the coordinates of the Hamiltonian are only r, the spin orbitals have space and spin part. So that spin part I am going to integrate. And you will see that this integration is trivial. So if we look at this integration, this chi can be phi 1 alpha, phi I, one of the phi's alpha or beta. Both left and the right are same chi I. So if this is alpha, this is also alpha. If this is beta, this is also beta, which gives you always 1. So I will have, in terms of space orbital, 2 times I phi I h phi I. Is it clear? Where I now goes over n by 2. That is important. So each of these spin orbital is derived from the 2 space orbitals. Each case, the integral that survive is only in space coordinate, phi I h phi I. The spin part is 1. So the first part is quite trivial. Now we look at the second part, plus half. Now I do the same exercise here. So chi I is 1, this chi I is 1. Whatever is the spin orbital here, the same spin orbital occurs here. So if it is alpha, this is also alpha. If this is beta, this is beta. Similar thing happens for j. This can be alpha, this can be beta. So if you write it in terms of the space orbital, the same expression, ij, n by 2 now, then how many combinations will survive? 4. This can be alpha independently, this can be beta, this can be alpha, this can be beta. So 4 combinations will survive. Each of them can be alpha and beta independently. So alpha alpha alpha, alpha beta alpha beta, beta alpha beta alpha, beta beta beta. Is it clear? All will survive because the integrations are taking place like this. Again, remember, it's all Dirac integrations. In terms of coordinates of electron, it's 1 2 1 2. Okay? So coordinate of electron is 1 here, 2 here, 1 here, 2 here. And these are complex conjugate normally, but let's assume that everything is real orbital, then the symmetries become easy, but doesn't matter. They can remain complex, they can remain conjugate, complex. So 4 times this will survive. And this will then become phi I phi j 1 by r1 to phi I phi. Is it clear? This is again a Coulomb integral, but now in terms of space orbitals alone. That is the only difference from this Coulomb integral. Interpretation is exactly same. But in terms of space orbital, this comes with 4 times, but of course there is a factor half. So let's not forget that. We'll bring that factor half later, after analyzing the exchange part. In the exchange part, however, if this is alpha, this need not be alpha. But remember, this is 1, this is 1. So if this is alpha and this is beta, it becomes 0. So out of those 4 combinations, 2 will not survive. So only thing that will survive is alpha 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 or beta beta beta. If this is alpha, this is beta, then it becomes alpha beta beta alpha, and that's 0. because alpha beta will be integrated, right? Or beta alpha will be integrated. So only twice this exchange term will survive, and giving you phi I, phi j, 1 by R12, phi j, phi I. So in terms of special orbitals, this will be my final expression. It's very, very easy to do. This procedure of deriving this expression from this expression is what is called spin integration. I hope it is clear what is spin integration, that I have integrated only the spin variables. And once I have integrated the spin variables, the spin orbital becomes an expression in terms of spatial orbitals. Is it clear? So this part for the closed shell, I can now write the final expression and give them a name. So energy becomes sum over 2 phi I h phi I. This is very easy to see. There are n by 2 spatial orbitals, so there are n by 2 1 electron integrals. Since there are 2 electrons in each of them, you are multiplying by 2. That's how this 2 has come, alpha and beta, right? So that's the interpretation. Plus sum over ij. Remember, I have picked up this first form, half of all I all j. So remember that. 2 times Coulomb integrals. Phi I, phi j, phi I, phi j. This is ith orbital interacting with the jth orbital. But space now, not spin. So remember, these are space orbitals. I call these 2jij. So this is a Coulomb integral involving phi I and phi j. Moment I say it's a Coulomb integral involving phi I, phi j, you should be able to write the actual integral. Since it is Coulomb, it must be phi I star phi I, phi j star phi j. So you should be able to write ij, ij in this lexical form, Dirac notation. Right? Ij, ij essentially mean I star and I here are 1, 1, j star and j here are 2, 2. I read it from the left to right as ij, ij. Is it clear? And that would be simply written as j subscript ij. This is another common notation, so I am just introducing it. Half into 4 becomes 2. Then I have half into 2 minus, and I call this exchange integral kij. This is again just a notation. So if I write kij, this means ij ji. Lexical order you read ij ji. I hope all of you are not understanding. It's just simple way to write. If I write kij, you should be able to write the integral. If I write k12, we should be able to write the integral. So that becomes a very simple form for a closed shell in terms of spatial orbitals. So of course, this is n by 2. The summation index change now. The number of spatial orbitals at n by 2, which actually came from the n spin orbitals. Here, these are n, and the process of spin integration gave you n by 2. Is it clear? Is it clear to everybody? Okay, good. Now you see for I equal to j, just like in the spin orbital I noticed that chi I, chi j, the spin orbital was identical, so it was 0. But here it is not exactly 0, because jii is equal to kii indeed. jii is ii, ki is ii. That is equal. But unfortunately in the energy, I equal to j survives as one term. So this becomes now 2 times sum over I n by 2 phi I h phi I. For I equal to j, there is one term which survives, jii. Because one jii cancels one kii, one Coulomb term survives, which is actually not surprising. Spin orbital, nothing would surprise because they are space orbitals. So there can be 2 electrons sitting in the same space orbitals, they will have a Coulomb interaction. So this is not at all surprising, because we are rewriting this expression in terms of space orbital. In terms of spin orbitals, this could never have survived, because no 2 electrons can be sitting on chi I, because of the Pauli principle. But in terms of space orbital, there can be 2 electrons, of course, albeit one of them would be alpha, one of them would be beta. That is clear. Because now my information of the spin is gone. I am just saying Ji, but it is clear that they are opposite spins. For the self, they are opposite spins. Then I equal to J is gone. After that, I can write the rest of them, which is I not equal to J, 2 Jij minus Kij. Note again, by the similar argument, Jij is equal to Jji. Kij is equal to Kji. That is, if I interchange I and J, the J and K remain the same. That's the same argument. That is basically because 1 and 2 electron coordinates are dummy variable. So that part is still correct. So I need not write, I can only write I less than J and multiply this by 2. I can say 4 Jij minus 2 Kij, I less than J pair. Okay? So there are several expressions that you can write again because of symmetry, but remember that this comes out separately. Or you can continue to write this and then simplify as and when required. It doesn't matter. I am just kind of showing you.